Alright, in the last video we had gone through stages 1 through 4, and so now we're looking at the moment where we can just barely find some of these protostars on the main sequence. This is, notice this evolution that we're talking about is going to be stars that are going to become like the sun. So basically, eventually become one solar mass stars. So notice the size of it. This thing is more than 100 times the size of our sun at this particular stage, which makes sense. Remember, it started out many parsecs across. These things aren't necessarily spherical. As we saw with the situation with magnetism, can actually distort these things. So you're getting different shapes of clouds. Anyhow, at this stage, so once they get about this size, they're definitely becoming more and more spherical. And then, of course, when they become stars, they're very spherical. So they're representing these as spherical. So stage 1 is this gigantic cloud. Here's stage 2. And stage 3, and 3 through 3 and 4, and so forth. So they're just kind of showing it. So a big thing to talk about is this idea of equilibrium, right? So what happens with the protostar is it's heating up, and it gets hotter and hotter and hotter. So let's see, we need this stage right here. It gets hotter and hotter, and it's not heat due to fusion, right? Because it's not a star yet. It's a protostar, right? That's literally what we mean by protostar. So what's happening is matter is falling into the star. Actually, this is a bad example right here, because there's actually matter flying out of the star in a bipolar fashion. Usually there's a strong magnetic field associated with this, but think of the matter that's coming in these directions, right? It's falling onto the star, and that is causing it to heat up, and also, of course, as the matter gets closer, it gets more dense. It becomes, there's more of a gravitational collapse. They're showing the amount of time for each of these stages. So that was in that table that we first looked at too. So this is. After stage 4, it drops down to, let's see, so we just went over stage 5. This is stage 4. So stage 5, it begins to collapse, and gravitationally collapse, and is heated from material falling onto it. And sometimes these magnetic fields, as I said, are so strong you'll actually have matter streaming out, charged particles in the direction of the magnetic poles, the north and south poles. All right, so here we are, or we were at stage 4. We're dropping down to this is the collapse taking place, and notice we're going from roughly 100 times the radius of the sun down by a factor of 10, right? And so it's now only 10 times the size of the sun. So that's stage 5. Stage 6, it's getting closer to the size of our sun, but still a lot bigger. So in the last stages, you can actually see this happening on the HR diagram. Remember, we never look at one particular star. I want everybody to understand that. You don't ever, there's not enough time. I mean, humans have been observing the night sky for maybe a couple of thousand years, and that's just with the unaided eye. I mean, with telescopes, it's been, about 400 years, and telescopes of any real significance, it's only been about the last 200 or even 100 years, with modern electronics to actually make very accurate measurements. You're talking about maybe 100 years of data. So there's no way that there's enough time to follow these stars from stage 4 to stage 5 to 6, and then ultimately dropping onto the main sequence which is the last, the final stage, stage 7. So what we do is we look at multiple stars at different points, at different stages, or protostars, I should say, before they reach the main sequence. They're protostars, or actually right before they reach the main sequence, they become stars, and then they'll settle down and drop onto the main sequence and just stay there, right, until they die, basically, and which in some cases is billions and billions of years. For stars up here, it's only maybe hundreds of millions of years. Stars way down here, there hasn't been enough time in the age of the universe for some of these stars to leave the main sequence, because they're perfectly comfortable going through their hydrogen fuel supply, but they're not putting out a lot of energy, right? There's not a lot of luminosity. All right. So anyhow, so the protostar. So one thing that I should mention, and this is a really important idea. So let's say that this step from 4 to 5 is more or less a straight line. So it's not exactly, but let's say it's almost a straight line. And so the temperature is exactly the same, but notice, even with the same temperature, maybe a slight rise in temperature, you get a dramatic decrease in luminosity, and the decrease in luminosity is literally just size. So you can have, let's say you had 2 stars on the main sequence, or sorry, 2 stars that have exactly the same temperature. Let's say 6,000 Kelvin. So there could be a star right here on the main sequence. There could be a star up here in the giant phase. They both have the exact same temperature. The only thing that's different about them is their luminosity, right? And so the only way to explain that, for 2 stars to have identical temperatures, right? So they, the temperature would be where these things would cross. Like if you draw a straight line down from where the star is to the horizontal axis, the temperature axis, and then you go up, and let's say there's another star up here. How could those 2 stars have the exact same temperature and have vastly different? Let's say this one, if there was a star right here, it would have a luminosity of 1, and then if there's a star straight above it right here, it would have more than 100 times the luminosity of the sun. The only way to explain that is size. So that's it. The bigger a star is, the more luminous it is. Given the exact same temperature, but different luminosities, and in fact that's how we know about these things over here, which are called white dwarfs. They are extremely hot. These things are up around like B stars and O stars, but they're way down here in luminosity because they're tiny, they're small, they're physically small. All right, so getting back to the stages. All right, so we've begun to collapse, and so we're down here we're heading towards stage 6. So we're still bigger, larger than the sun, than our sun, and let's see. So let's talk about this. All right. So one thing that I should mention is this stage 4 to stage 6. This is actually named after a person, a Japanese astrophysicist, Hayashi. It's called the Hayashi track. He did a lot of the astrophysical work on predicting what this track would look like, on the HR diagram. And of course, this is in very good agreement with what is observed. So both the theoretical and the observational science agree to it pretty remarkably, as we're going to see. All right. So, at stage 6, the core reaches, and I guess I should say something about this. It's pretty complicated what exactly is going on. I mean, there's a lot of astrophysics going on for when this happens. So, all right. So anyhow, in stage 6, the core reaches roughly 10 million Kelvin, and that is the point where the nuclear fusion can take place. And so in stage 6, notice we're still just slightly off the main sequence. But that is the point where the star, the protostar, becomes officially a star. All right, and then this now brand new star continues to contract and increase in temperature until it reaches equilibrium. And when it goes on to the main sequence, in fact, there's a theoretical point that it will fall onto the main sequence, which is stage 7, and that's actually, it's got an acronym. It's a very one of the nice acronyms in astronomy. It's called ZAMS. So it's Zero Age Main Sequence Star. ZAMS. All right. Let's see. Did I mention that? I don't see that mentioned here. Anyhow, ZAMS would be the theoretical point where the star would, if you follow this track, the Hayashi track, that leads to this theoretical point where the star ends up on the main sequence. And of course, these the theoretical and the actual observable evidence shows that they're in complete agreement. All right, so really what happens is after stage 6, the star has to settle down. It has to reach a final equilibrium, and then when it drops onto the main sequence, it stays there. It doesn't go anywhere. I know I've mentioned that already in one of the other videos, but it does not stay there. I'm sorry, it doesn't move once it's on the main sequence. All right, until it's dead, until the star can no longer turn hydrogen into helium. All right, so again, stars way up here, really massive, very luminous stars, they leave the main sequence in a matter of millions of, maybe hundreds of millions of years. As you get towards the sun, stars are just on the main sequence, just above the sun. Let's say maybe 5, 6, 7 billion years. The sun, we're talking about 10 billion years, and then more than that for these stars way over here, like in the M stars, these really tiny little M stars. All right, so that is the 7 stages. Let's see, the main sequence. So this is a really important idea. The main sequence is a band rather than a line. So stars, when they reach the main sequence, they're going to arrive at different locations because they're made of slightly different, different. It's all atoms in the universe, of course, but in different concentrations. Some of them might have a little bit more carbon, some might have a little more oxygen, and so forth. It's just random, and so that where they end up on the main sequence is going to be a little bit different. But once they're there, they don't move. Okay, so that's like really important. You gotta understand that. All right. And so because they're in equilibrium, they're turning hydrogen into helium. All right. What about stars of more massive? You certainly know that there's stars that are much more massive than our sun. What happens to them? So the fragments. Some fragments are too small to I'm sorry. But before we get to the more massive ones, let's talk about what are eventually going to become brown dwarfs. So fragments that are smaller than they won't accumulate enough mass to ever become a star. So what happens to these things? We think that these you have to have about 0.08 the mass of the sun, which is about 80 times the mass of Jupiter, or lower. They're not going to become their